if I told you that you could predict roughly what a thunderstorm will look like hours before it even exists at all, from one simple piece of information? Well, perhaps that's a bit hopeful, but in this video we're going to try it anyway. The one piece of information I'm talking about is our old friend the weather balloon, and we'll be verifying our guesses using time lapses of Hector thunderstorms from October of last year, 2016. And for those that want to play, this video acts as a game where you can pause and make a sketch of what you think the thunderstorm will look like. After that, I'll reveal the thunderstorm time-lapse. So first of all, let me tell you what Hector is. Now, a lot of this background stuff I've been through in previous videos, so look for those little eyes in the top right for more information. And I'm really going to whiz through it fast here. Let's fly into Northern Australia and imagine a place where in the glorious hot and humid afternoons of most days in October, November and December, you had a view across a beautiful strait of water to a distant towering thunderstorm. Well, this is what you get from Nightcliff, a northern suburb of Darwin, because about 50 to 140 kilometers away lie the large Tiwi Islands, home of the Hector afternoon thunderstorm. Basically, as the sun rises in the day, it heats the land much faster than the ocean, and the sun also heats the surface of the earth much faster than the air above it. And for the Tiwi Islands, this means that the air near the surface over the islands warms much faster during the day than both the surrounding ocean and the atmosphere above. This generates sea breezes that move in from all coasts and collide, forcing air upwards into an often unstable troposphere, leading to explosive thunderstorms called Hectors. Here in the tropics, the troposphere, which is the layer in which most of our familiar weather occurs, is actually quite thick, and the thunderstorms are often over 15 kilometers deep. Very quickly and simply, to understand how we might be able to predict what a thunderstorm will look like, we need to mention a couple of points. Firstly, warm air rises when surrounded by cooler air, and a growing thunderstorm is basically a large amount of warmer air rising through surrounding cooler air. It's the same reason why hot air balloons rise up, simply because warmer air is less dense and lighter than surrounding cooler air, so it rises. But secondly, and more importantly for this video, clouds are usually pushed in the same direction as the wind. So the thunderstorm may get pushed around by different winds at different levels, which will change what the thunderstorm looks like. As discussed in an earlier video, these differences in winds, known as wind shear, can cause a thunderstorm to last much longer and produce more severe weather. But here we're mainly focused and interested in how the winds change the shapes of the clouds. So to have any hope of guessing what a thunderstorm will look like, we're going to need to know what the winds and what the temperatures are throughout the troposphere. And to get that information, we need the great and wonderful information from the weather balloon. The weather balloons we're going to look at are launched from Darwin at 000 Universal Time, which is 9:30 a.m. in the morning, Darwin time. The weather balloon measures temperature, dew point temperature, and the winds as it rises up through the troposphere, and then into the lower stratosphere. This info is then plotted on a somewhat confusing diagram like this. It's called a skew T. The first thing to understand is the scale of the diagram, so I've shoved in Mount Everest on the left. And now, the air in these types of afternoon thunderstorms originates in the lower troposphere, quite near the surface, and it's caused by the surface heating up during the day, so it warms that air that then fuels the thunderstorm. So we need to know what the temperature of that air will be as it rises up through the troposphere to see if it will be warmer or colder than the air around it. And if we can figure this out, then we'll know whether that air will continue to be more buoyant than the air around it and rise up. This hypothetical temperature is calculated and shown on this third line on the diagram. So, by comparing with this temperature with the temperature actually measured by the balloon, all of this red area indicates where a blob of air that rises from the surface will be warmer than the air around it. And this warmer air will be less dense and therefore more buoyant than the air around it. And this means that the blob of air will continue to rise up. It's fundamental for understanding thunderstorms, but it's pretty simple. Warmer air rises when surrounded by cooler, and we can calculate what that temperature of that air will be when it rises from the surface. Finally, and most importantly for this video, are the measured winds from the weather balloon, which are here on the right. These are oriented as on a compass, shown on the right. The side with the line sticking out indicates where the wind is coming from, and the number of lines that are sticking out indicates its strength. So you can get a quick idea of where the winds are coming from at all the levels in the atmosphere and also their strength. So let's roughly put this on as the red arrows. So with the red area indicating the slab of atmosphere through which the thunderstorm is expected to grow through, and the winds indicating the direction of the clouds in which they may be pushed, let's overlay an extremely dodgy cartoon of what this thunderstorm might look like when viewed from the south, which is the viewpoint from which the time lapses were made. You might also have noted that there's a small area of blue on the diagram. This shows a layer of atmosphere where rising surface air will actually be cooler than the air around it. And in this layer, lifted surface air will tend to sink because it will be more dense than the air around it. So it's effectively a barrier to reaching the more unstable air that lies above it. In fact, this blue area is known as convective inhibition, and it's very important because it can hold off thunderstorm development until later in the day when the surface temperature has risen substantially and the atmosphere has become more unstable. We can add another line to indicate just how unstable the atmosphere would have to be to overcome this blue area. This gives us a much larger orange area, indicating that with enough surface heating during the day, the blue area could allow the atmosphere to become more unstable, and for the thunderstorm then could extend to higher elevations where the winds are different. Therefore, taking account of this, the thunderstorm could extend all the way up into those high altitude westerlies. So we need to add this to our cartoon of the thunderstorm. Et voila! Question is, did the thunderstorm on this day look anything like this? Now we'll be returning to this case later in the video, so we'll see how it matches up with this pretty dodgy, rough prediction. Now the following time lapses are viewed from the south, so westerly winds should push clouds to the right, and easterly should push them to the left. Overall, for the following cases, just look at the red area, and then look at the winds, and if you feel like it, try and make a sketch of what you think the thunderstorm will look like. I'll prompt this with a bit of a pause title or something at the point in the video to pause and make a sketch if you feel like it. But enough rambling, let's get started. I travelled to Darwin in October 2016 and began time-lapsing the thunderstorms from Nightcliff. So let's get on to the first case, 20th of October. Now this one and the following day, 21st of October, are basically failure cases, but they're good for an introduction. And after that I'll let you guess the shapes of the thunderstorms for the remaining cases. Here's the morning sounding for 20th of October. You can see the red area, it's unstable, and while this red area extends to 10 kilometers of altitude, a little bit of surface heating, and with that little blue bit at the bottom, you can imagine it extending much higher to near 14 kilometers altitude later in the day. The winds show a layer of easterly winds below 4 kilometers, and then there are westerlies above, so you've got this big shift in winds as you go up through the troposphere. So in this case, we'd expect the clouds to be moving to the left at low levels in that easterly flow, and then with the upper part of the thunderstorm forced off to the right. So let's take a look at the time-lapse. In the time-lapse, the clouds in the foreground are in that low-level easterly flow, so sure enough, they are moving to the left. But in the background, you can see the distant deep convection over the islands, and that cloud is then moving to the right in the westerly flow at higher altitudes. Immediately, this knowledge opens up our perception of this seemingly mundane scene, because we know from the weather balloon that those distance clouds must be stretching to well above 8 kilometers altitude, because they are moving in the eastward direction in those westerly winds, which the weather balloon showed us are only blowing above that altitude. The second try was the next day, but again it was a failure. As with the previous day, the soundings showed low-level easterlies and upper-level westerlies, but a notable difference is that between the altitudes of 4 and 8 kilometers there was a slab of northerly winds. Clouds pushing into this layer should be pushed southwards towards Darwin, and therefore we might expect a layer of clouds to be moving in that flow towards the camera. In fact, this layer of cloud is quite clear, and unfortunately it also obscured the developing storm behind, which is why this case was a fail. Now we come to what I would call the first successful case, and for this one I'll show the sounding and winds, and then there will be a pause prompt so you can make a guess as to what the Hector thunderstorm looked like before seeing the time-lapse. The sounding shows decent instability that would further increase as the land warms during the day, because remember this is at 9:30 in the morning. The winds are a bit of a mess, but I want to focus on the layer of west to northwesterlies between 4 and 7 kilometers. And there's a sharp transition to easterlies at around 7.5 kilometers altitude, with light winds then above 10 kilometers. And finally, above 14 kilometers, there are nice decent 40-knot easterlies. If the top of the thunderstorm were to punch up to those altitudes, we would expect the anvil to spread off to the west, so to the left in the time-lapse, and that's a hint. So now pause the video and make your challenging guess as to what this thunderstorm looked like from the south, with a little sketch if you like. The lower layers were not clearly visible, so just do the upper layers above, say, 5 kilometers. Okay, so now looking at the time-lapse. First of all, the thunderstorm can be seen on the right, and it gradually moves westward, that's to the left. With the lower levels, they're a bit hard to see, but the upper part is clear. The most obvious feature is the top of the thunderstorm, called the anvil, shooting off to the west. But looking at the zoom time-lapse, we can see the effects of those shear layers in the sounding that we saw. Individual updrafts are getting sheared westward before stagnating in the calmer winds above. The time-lapse had to be ended there because I was hit by a torrential downpour, but it was a classic case of early development over Melville Island, moving to Bathurst and maturing into a large Hector. Things were a bit different on the 27th of October. In particular, the sounding shows a huge slab of atmosphere with 10 knots or less of wind. This layer of light winds stretches from about 5 kilometers altitude all the way up to 13 kilometers. At the top of those light winds is a slab of northerlies, and we know from the earlier 22nd of October case that northerlies tend to push the clouds towards the camera. So now let's pause again and you can try and make a quick sketch of what you think this thunderstorm looked like. Right, so here it is. A juicy, rapidly rising updraft develops. In those weak winds it rises vertically, and we can see the anvil pushing out towards the camera in those northerly winds we saw in the sounding. Did your sketch look anything like this? Here's the closer zoomed view. Notice how the very low clouds are moving nicely in that low-level easterly flow we saw in the sounding, and above that, a beautiful vertical convective updraft through that huge light wind layer. Then at the top, the anvil clouds wafting out towards the camera. Later, a separate thunderstorm developed over Bathurst Island. So now let's move on to the 28th of October. What was next in store for Hector? Well, this is a good time to introduce another key feature that the weather balloon reveals to us. This layer here is called an inversion. It's a small layer where the temperature actually increases with height. This is a very stable layer, which is indicated by how the red area nearly disappears at this point as you go up. Also, we can see a significant shift in wind direction close to the inversion level, so any clouds struggling to get through that layer should show a sharp change in movement near the top of the small clouds. We might expect a lot of clouds down low struggling to get through that layer, but when a strong updraft does, it might continue upwards, getting sheared slightly to the east and then to the west. At anvil level, there are west-southwesterlies and light winds above. Right, let's bring in the time lapses. The inversion cap is shown roughly as a blue dashed line, and the earlier clouds can be seen to struggle to get above this layer. But as the convective energy builds down low, the plumes begin to burst through the inversion layer, but the earlier ones get sheared and die in the dry air above. Eventually, the convection is strong enough to consolidate into thunderstorms. The upper levels of the thunderstorms move off to the right and away from the camera in the upper level west-southwesterlies seen in the sounding. At one point in the time-lapse, a lone plume bursts through the inversion layer. It gets sheared beautifully by the different winds we saw in the sounding before it evaporates in the dry mid-tropospheric air. You can also see a hazy region descending out of the upper cloud part. At these elevations, the temperatures are below freezing, and this precipitation is snowfall. Later, as thicker, stronger convective plumes develop above the inversion, we see another friendly cloud, the Peleus Cap Cloud. And finally, several thunderstorms develop over the islands, with the upper parts blowing off to the right in the upper level southwesterlies. Our second to last decent case of October was on the 29th of October. On this day there was a clear dividing line between the mostly easterly flow below 8 kilometers altitude and the southwesterly flow above. These two flow layers are apparent in the time-lapse, with all the early lower clouds moving in that easterly flow before the deeper convection develops into the southwesterly upper-level winds that push the clouds to the right and away from the camera. The first large thunderstorm developed over Bathurst Island on the left. Then a second develops over Melville Island. Finally, a huge, powerful updraft develops in between the two. The other thing worth noting is this band of high cloud that moves off to the west. I'm not exactly sure what this is, but I think it might be a gravity wave on the boundary between the troposphere and the stratosphere, caused by the vigorous thunderstorm updraft punching the lower stratosphere. And finally, we come to the end of the month, the 31st of October. The sounding on this day looked similar to the previous case on the 29th of October, with a clear divide between low-level easterlies and upper-level westerlies. Well, as you might have guessed in your sketch, this case looks very similar to the previous case. And can you spot another possible gravity wave? Or is it just deep cloud that punches briefly high enough to reach those high-level westerlies? I don't know. The general thing that you should be caught in a guess of what this and the previous thunderstorm should look like is that they should clearly be tilted to the right in such a distinctive shear profile. And that's it for the moment. As we head into November, HECTIME got many more exciting cases, including an atmospheric bore-triggered Hector. So please stay tuned and I'll get the November segment up. Thanks for watching.